The heuristic argument that led to the definition of conditional density was this. Now there are so many approximate equalities. Naturally, we feel rather uncomfortable with all these approximate equalities and start asking the question, is this any good in terms of rigorous mathematics? In this video, we are going to convince you that yes, this indeed can be dealt with rigorously. We have already seen the theorem of total probability in our Prob 1 course, where we are interested in probability of some event A occurring. Now A can occur in a number of different ways via path B1 or B2 up to Bn. So these events Bi's are mutually exclusive and exhaustive. So one and exactly one of them must occur. In that case, we can find out that A has occurred by summing over all the paths. For example, let's look at this path. This is probability that B1 occurs, and this says that A has occurred given that you are at B1. Similarly for all the other paths, and then we had probability A is sum over this product for all the individual paths. Now, using conditional density, we can have a similar result which we can actually prove. Suppose we have the random variable x and we are interested in knowing whether x lies between sum A and B. Now, there is another random variable jointly distributed, and this represents the continuum of all the values that y can take. It's a continuous thing. So, y has some value and x takes some value. I am showing them with dotted lines because there is a continuous spray of values. In that case, just as we had probability Bi here, we will have the marginal density of y. Similarly, once you have this y, what is the chance that this will happen? And that is given by the conditional density. Of course, we have to integrate over a to b. I am not writing that because there is not much enough space. So if I just imitate this idea, I should get, instead of the sum, I should get an integral. Then instead of this, I should get the marginal of y. Instead of this, I should get the conditional density. So let us write it down, just imitating the pattern, and then we'll see whether we can prove it rigorously. I have the integral, multiplying with the marginal, integrating with respect to dy, and this is what I have written over here. Now I have written the integral explicitly. This does not look very nice. It would be nice if I take all the integrals to the left. Anyway, the inner integral is with respect to x, and this behaves like a constant, so I can take the integral sign here to get this thing, the integral from minus infinity to infinity. This is for y, integral from a to b, this is from x. I am multiplying the marginal of y with the conditional density of x given y. Now I can do something more interesting also. I may not allow y to take all possible values minus infinity to infinity. I can restrict its value to some particular subset, in which case I will get probability x in a to b and y in c to d. Now the outer integral goes from only c to d and the rest of it remains the same. So I just obtained it by imitating the conditional probability diagrams that we used to get for discrete cases. Now I claim this result is indeed true and can be proved rigorously without using any of those heuristics, and in fact the proof is trivial. This integral is just same as this. I have replaced this by its definition. That's all. Immediately you can see that these two things cancel. So you are basically taking the joint density and integrating it over a to b and c to d, which immediately gives you this quantity. That's the definition of joint density. So you see, it's just a one-line proof. So the particular quantity that we define based on heuristics indeed serves the purpose, and this is really called the theorem of total probability in case of densities. Now we are using the term conditional density of x given something. Is this really a density? When I say is it really a density, I mean density in X. Now, and the answer is yes, it is. Now, how do you check? Well, we shall check the two most important properties. Number one, is it non-negative? Of course it is, because the ratio of two non-negative quantities, and this is positive by assumption, so this must be greater than or equal to 0. The second question is the integral equal to 1? Here I am talking about integral with respect to x. Just by plugging the definition of the conditional density, I get this. This quantity is a function of y alone, so behaves like a constant with respect to x and comes out of the integral. Now we notice that this is precisely this by definition. You get the marginal density of y by integrating out the other variable x, so these two things are the same, and this is anyway non-zero, so they just cancels each other out and gives you 1. So this does satisfy those important conditions, non-negative, and the integral is equal to 1. Now, since the conditional density is a density, so you can define expectation, variance, moments, etc. all with respect to the conditional density, and the resulting thing will be called conditional expectation or conditional variance or conditional moments. For example, this is conditional expectation of x given y, just the definition of ordinary expectation, except that I am using this thing. And here also you have all the old stories like if it is non-negative, then you can use this. If it is negative and positive, you will take the plus part and the minus part separately. All those discussions apply exactly in the same way, except that in place of density, you are using the conditional density. For example, this is conditional variance of x given y equal to y. This minus this means expectation whole squared. Now all these things are exactly as we did in our last semester. The only thing that has changed is instead of conditional PMF and summation, we are using conditional density and integration. All the properties etc. that we studied are still valid. For instance, let's take a look at tower property that we had seen in last semester. Now the setup is using density, xy as joint density fxy, and let x given y with a conditional density of x given y equal to y, just the usual notation. Earlier we had worked with simple random variables, so everything was finite, but now we have to impose the finiteness restriction explicitly. So I assume this conditional expectation and this expectation both are finite. And when I say this, I mean for all values of y. Then if you take the conditional expectation and take further expectation of that with respect to y, you will get back the unconditional expectation. That was the tower property. The proof is very simple. I am first looking at this thing that by definition is this quantity. Now I am taking expectation of this with respect to y, which means I am going to integrate this quantity from minus infinity to plus infinity with respect to y. I will take this value, multiply this with density of y, which is fyy. Now since this inner integral is with respect to x and y, it is completely based on y, I might as well insert it over here. So I will get fyy dx dy. Now just use the definition of this. The definition was joint density divided by marginal density, fxy divided by this marginal at y. This and this nicely cancels out, and this is exactly the definition of expected value of x. So we have shown that the two sides are equal. This exercise is to give you an idea about the power of the tower property. So I am giving you xy uniformly distributed over S. I have already shaded S for you. X going from 0 to 1 and y going from 0 to x. Your job is to find expected value of y. Of course, you can find expected value of y integrating etc. etc. Not that difficult, But if you use tower property and some little mental math, you can just stare at the picture and immediately say that this will be the answer. Try to get that technique.